Welcome to the Neuron Story. We begin with a neuron who is the main character of our story, and we're in the preamble. So a neuron has both a receiving end and a sending end. As illustrated here, we have cell A, which is a sensory neuron located in the knee, cell B, which is an interneuron located in the lumbar region of the spine, and cell C, which is a motor neuron located back at the knee. Here we have the axon terminal of cell A. We have the synapse between cell A and cell B. We have the dendrites or the dendritic arborization of cell B, the soma or the cell body. Here's the axon hillock, and then we have the axon shaft, and here are the nodes of Ranvier. And then we have our glial cells that are covered by myelin sheath. And at the end, we have our axon terminal and the terminal buttons of cell B. And then here are the dendrites or dendritic arborization of cell C. So we go on. An event happens in cell A, and we have a neural network, which is a neuron with two synapses, a presynaptic membrane and a postsynaptic membrane. The presynaptic membrane is located at the axon terminal of cell A, and the postsynaptic membrane is located at the dendritic arborization of cell B. So when an event happens at cell B, there's four things that can happen in the synapses between cell A and cell B. One is dissipation, where the neurotransmitter floats away. And next, there's degradation, and that's when the neurotransmitter is rendered mute. Next is reuptake, and that's when the neurotransmitter is recycled or is taken back into cell A. And then four, and what we're interested in this story, is that it binds to the postsynaptic receptor. It is important also to know that there is fluid both inside and outside of the cell. Inside of the cell is called cytoplasm, and outside of the cell is called interstitial fluid. These are two key characters because the ions they contain, think of them as a river that holds these characters close. There's a difference in concentration in three key ions in the cytoplasm and interstitial fluid. They are sodium, potassium, and chloride. The way that I know that there is actually a difference in the concentration between these ions and their movement across the membrane is that I have technology that is hooked up to this system via an oscilloscope and microelectrodes. So now on to the next stage. Synaptic vesicles empty into the synapse between cell A and cell B. The postsynaptic membrane is actually made up of a lipid bilayer. So outside of the cell is interstitial fluid, and inside of the cell is cytoplasm, remember. The membrane between these two is the lipid bilayer. Most of the time, between these two, the lipid bilayer has receptors that span the lipid bilayer. Most of the time, the receptor is actually closed because there's no transmitter that is bound to it. But when the neurotransmitter, also seen here, also seen here. When the neurotransmitter is released from the presynaptic membrane, goes into the synapse, it binds to the binding site located on the ionotropic receptor located in the postsynaptic membrane of cell B. And this particular ionotropic receptor is permeable to sodium. So when a neurotransmitter binds to this site, sodium is allowed to come through this channel, or this ion pore. Now, when sodium comes into the cell, it is able to do this through two forces. One is called osmosis, which is the force when particles in the solution go down a concentration gradient. And the other force is electrostatic pressure. So when sodium has a greater concentration outside of the cell than inside the cell, it would come into the cell. But both of these forces have to work. Sodium has a positive charge, and since inside the cell is actually more negative, opposite charges attract each other. The only way, again, to measure this movement is through an oscilloscope that also has micro electrodes hooked up to the postsynaptic membrane. Okay, where did I go? All right. At rest, the cell at rest registers at -70 millivolts on the oscilloscope. If the neurotransmitter were to bind to the receptor binding site, then the receptor would open the sodium, and then the sodium would enter into the cell. And here we would see on the oscilloscope a rise, a slight bump. This is called an EPSP. An EPSP registers the depolarization or more positivity of the cell due to the entrance of sodium. EPSPs are created when ionotropic receptors located on the dendrites of cell B are opened due to the presence of neurotransmitter binding to the binding site on these ionotropic receptors. Now, on to the good stuff. Now we got some new news. So when there's a lot of neurotransmitters, multitudes of cell B, the neurotransmitter molecules add on to each other, and in adding to each other, they add more positivity to the cell. They then reach the threshold of excitation because of these many EPSPs, which is at -75 millivolts. This process is called temporal summation or spatial summation. This entails that an action potential is beginning. The location of the receptors that cause the threshold of excitation are located at the axon hillock of cell B. The axon hillock collects the the collection of, or the summation of all the small electrical potentials on that causes an opening of the voltage gated sodium channels. These channels look like ionotropic receptors, but there's no place for neurotransmitters to actually bind onto these voltage gated channels. The voltage gated channels require a multitude of voltage caused by neurotransmitters binding to sites that have been opened. Once the negative 65 millivolts threshold has been reached, that is the initiation of the action potential at the axon hillock. The axon hillock is generated from the rest because of the summation of EPSPs reaching the threshold of excitation. Then there's a massive influx of sodium coming into the cell that it reaches positive 55 millivolts, which is called massive depolarization. At that point, sodium will reach equilibrium, but the potassium grates open. Since the cell now is very positive, the potassium inside the cell is now very, very positive. Like charges repel each other, so the potassium will leave or exit out of the cell. This causes a large and steep hyperpolarization of the cell. So we have the upswing and downswing of the action potential. Sodium is trying to reach its equilibrium point at negative 75 millivolts. And when it does briefly on the cell itself brings the sodium potassium pumps on the cell, brings it back to rest. That's where it is. Brings it back to rest. All right. The action potential obeys the all or nothing response. It happens in discrete places such that it starts at the axon hillock when it reaches the edge of the myelin sheath. It then spreads like a wave to the node of Ranvier, to the next node of Ranvier. For each node that would have a sodium-potassium gated channel, allowing sodium coming in and the potassium going out, the action potential would be generated at that node.